Hi everyone. This is the last little video in the first chapter, and we're going to look at exact values and angles of inclination. We'll start with exact values. Although sine, cos, and tan ratios can be measured from a unit circle or from a graph of a sine, cos, and tan curve or with a calculator, some values can be determined using Pythagoras and trigonometric ratios, and by an examination of a graph without a calculator. So let's see if we can get a hold of these exact values, and they're typical of questions that turn up in non-calculator sections. So on the left here we have an equilateral triangle of side 2 and a bisector from the top of the triangle, splitting this line in half. We're specifically going to look at this triangle here, and this is the one that you would write on the top of your page to help you find the exact values. We know that this angle here is 60 because it's an angle in an equilateral triangle. Because we've bisected the top angle, we know that this is 30, it's been cut in half. Now, because we've bisected this line here, what would normally be length 2, because all of the lengths on this equilateral triangle are length 2, this length here is 1. Now we can find some ratios out. If we wanted to know cos 60, because it's a right angle, we know that it's adjacent over hypotenuse, so cos 60 is equal to a half. There's one exact value that we now know. Cos 30, adjacent over hypotenuse, is going to be root 3 on 2. Tan 60, opposite over adjacent, tan 60 opposite over adjacent will be root 3 on 1, which is just root 3. And tan of 30, which will be opposite over adjacent, will be 1 on root 3. So there's 4 exact values that we now know and we can use. Sine 60 would be opposite over hypotenuse, which is root 3 on 2, and sine 30 would be opposite over hypotenuse, which is a half. So there's 6 exact values we know, all the exact values for sine, cos, and tan for 30 and 60. Similarly, for a 45-degree triangle of side 1, we know that, before we finish, I should say how we get this root 3 here. Given that this is a right triangle, Pythagoras can be used to find this side. So it would be 2 squared, take 1 squared, and then take the root of it. So that would be 2 squared is 4, take 1 is 3, take the square root of it is root 3. Thus we get this. So that root symbol is probably going a little bit too far. Okay, that's that one. Similarly, for this triangle here of sides 1 and 1, given it's a right-angled triangle, we can use Pythagoras to find the length of this side. 1 squared plus 1 squared is 2. Take the square root of it is root 2. Therefore, this length is root 2. And now we can find sine and cosine. So sine of 45, opposite over hypotenuse, 1 on root 2. Cosine of 45, adjacent over hypotenuse, also 1 on root 2. Tan of 45, 1 divided by 1 gives us 1. So now we have all the exact values for 30, 60, and 45 for sine, cos, and tan. We can also work them out for 0, 180, and 360 using the curves themselves. There's a neat way of doing it in the Sadler book using triangles, but I find the curves is usually a bit easier once you know them off by heart, and you should. So here's a sine curve from 0 to 360. We know that sine 0, sine 180, and sine 360 are all 0. We know that sine of 90 is 1 and sine of 270 is negative 1. From the cosine graph, we know that sine 0 and cos 0 and cos 360 is 1. Cos 180 is negative 1. And cos 90 and cos 270 are both 0. So all those values there. Now from a tangent graph, we know that at 0, tan is going to be 0. At 90, it's undefined, never quite reaches 90. And back at 180, it's 0 again. So given the 3 graphs and the 2 triangles, you can work out all of the angles listed in the Sadler book that you should learn off by heart. And I must admit, I've never ever learnt them off by heart. I've only ever learnt off these 2 triangles and the 3 graphs. If that's easier for you, great. If it's easier for you to learn off the values, learn off the values. It is strictly up to you. Now remember that the obtuse angles can be found using these properties here, as we did in the first exercise. Once you've done that, it'd be a good idea to stop the video, attempt exercise 1D, and then come back to this at the end. Or if not, feel free to watch it now and then you can do it afterwards. So, an angle of inclination. An angle of inclination is an angle that the line makes with the x-axis anti-clockwise, and we've seen this already kind of with the unit circle and obtuse angles. So in this case we would say the angle of inclination is from here to there for a graph with a negative gradient, and from here to here for a graph with a positive gradient. Where the angle of inclination is one of the values that we're familiar with from our exact values, we can use them to determine the gradient of the line. So given that it's gone 1 unit across and root 3 up, that will allow us to find the gradient, because that's all that the gradient is, it's the rise and the run. So for 60, the rise would be root 3, the run would be 1, therefore the gradient would be root 3. For 135, we know that from our properties here, cos of 135 is the same as negative cos 45. So here's 45, cos 45 is 1 on root 2, therefore cos 135 would be negative 1 on root 2. If we were looking for the gradient of 45, we know that it's 1 over 1, but in the in this quadrant here, the value of it would be negative 1 because you're on the negative side. So from here to here, it's not rising, it's falling. So this top value would be negative 1, even though that you're still going across 1. And that should help you do the exercises in 1E. Thank you, everybody.